Forget little green men. What would alien life actually look like? Last time, we went deep on the Great Filter. The idea that somewhere between simple chemistry and starships, something is killing almost every civilization before it gets started. Dark stuff. So today, I want to do something different. Let's assume life exists somewhere out there. Let's assume it got started, it survived, it evolved into something interesting. What would it actually look like? Not what Hollywood says. Not what the covers of supermarket tabloids say. What do evolution, chemistry, physics, and biology actually suggest? Because the honest answer is far stranger, far more surprising, and in some ways far more wonderful than anything the film studios have come up with. Let's get into it. First, let's talk about where our assumptions come from, and why they're almost certainly wrong. When most people picture an alien, they picture something that looks roughly like us. Upright, bilateral symmetry, one head, two arms, two legs, eyes at the front, a face, a mouth, usually about the same size as a human. Even in the most imaginative science fiction, aliens tend to be humanoid. Star Trek is the most obvious example, and the writers knew it. They even invented an in-universe explanation for why every species in the galaxy happens to look like a person in a rubber suit. Convenient. But here's the thing, that assumption that intelligence converges on a human body plan is not supported by biology. It's supported by budget constraints and the limits of human imagination. Let's use Earth as our laboratory, because Earth is the only planet we know of with life on it. And Earth is extraordinary. Life on Earth has been running for 3.8 billion years. In that time, evolution has produced an almost incomprehensible variety of body plans, sensory systems, and survival strategies. Consider the octopus. The octopus is one of the most intelligent animals on Earth. It can solve puzzles, it can use tools, it can recognize individual human faces. It has been observed unscrewing jar lids, navigating mazes, and, in at least one documented case, escaping from its tank at night to hunt in a neighbouring tank before returning before morning. And the octopus is about as different from us as it is possible to be, while still being an animal on the same planet. Its nervous system is distributed. 2/3 of its neurons are in its arms, not its brain. Each arm can act semi-independently. It has 3 hearts. Its blood is blue because it uses copper rather than iron to carry oxygen. It has no bones. It can change the colour and texture of its skin in milliseconds. And its eyes, which evolved completely independently from vertebrate eyes, are in some ways superior to ours. They don't have a blind spot, for instance. If you found an octopus fossil with no other context, you might struggle to believe it shared a planet with us. And the octopus evolved here, on Earth, with the same basic chemistry, the same DNA, the same evolutionary pressures. Now imagine what 4 billion years of evolution on a completely different planet, with different gravity, different atmospheric chemistry, different light from a different star, different temperatures, different timescales, what that might produce. Let's think about the basic building blocks. Life on Earth is carbon-based. Carbon is extraordinarily good at forming complex molecules. It can bond with 4 other atoms simultaneously, creating the long chains and intricate structures that biology requires. And carbon is one of the most abundant elements in the universe. So carbon-based life elsewhere seems genuinely plausible. But carbon is not the only option. Silicon is the most commonly discussed alternative. It sits directly below carbon on the periodic table, which means it has similar bonding properties. Silicon is also extraordinarily abundant. It's the second most common element in Earth's crust. The problem with silicon is that silicon dioxide, the waste product of silicon-based metabolism, the equivalent of our carbon dioxide, is a solid at most temperatures. Breathing out sand is not a great survival strategy on most planets. But on a world that is extremely hot, where silicon dioxide remains liquid or gaseous, silicon-based life becomes more plausible. A planet closer to its star, or one with a thick insulating atmosphere, might host chemistry we can barely imagine. There are other candidates too. Ammonia as a solvent instead of water, hydrogen fluoride, liquid methane, which is exactly what fills the lakes on Titan, Saturn's largest moon. Life that uses entirely different chemistry to store and transfer energy. We don't know if any of these actually work, but we have no strong reason to rule them out. Now let's think about what drives the shape of a living thing. On Earth, Body plans are shaped by a handful of key pressures: gravity, the need to find food, the need to avoid being food, the need to reproduce, the need to process information about the environment, which is where sensory systems come from. Change any of those pressures and you change the body plan. Take gravity. On a planet significantly larger than Earth, with stronger gravity, large land-based creatures would be crushed under their own weight. Life might stay small, flat, and low to the ground. Or it might never leave the ocean at all, because water provides buoyancy that counteracts gravity in ways air does not. On a smaller planet with weaker gravity, creatures could grow enormous, or fly with relatively little energy. The whole ecosystem might operate in 3 dimensions in a way that land-based Earth life mostly doesn't. Take the star. Most stars in the galaxy are not like our Sun. The most common type, red dwarfs, are smaller, cooler, and much dimmer. They emit most of their light in infrared rather than visible wavelengths. Life evolving under a red dwarf might have eyes, if it has eyes at all, tuned to infrared. It might be sensitive to heat gradients in ways we are not. Or it might have abandoned vision entirely in the dim permanent twilight of a tidally locked world and developed extraordinary sensitivity to sound, vibration, or chemical signals instead. Imagine a creature that navigates its world entirely through smell, that communicates through chemical signals rather than sound. That has no concept of colour, because colour in its world is meaningless. That creature might be extraordinarily intelligent. It might have complex social structures, language of a kind, technology even, and it would be so utterly alien to us that we might not recognise it as intelligent at all. This is actually one of the most under-discussed problems in the search for extraterrestrial intelligence. We tend to look for intelligence that resembles ours. We listen for radio signals. We look for structures that reflect our own engineering, something built, something geometric, something that looks like it was made on purpose. But what if intelligence elsewhere doesn't build in ways we recognise? What if a civilization that evolved from chemical communication rather than sound has no concept of radio? What if their technology is biological rather than mechanical, grown rather than constructed? What if the most advanced civilization in the galaxy solved its engineering problems by engineering life itself, and their greatest achievements look to us like unusual ecosystems rather than cities? We would fly past them. We would study them as biology. We would never know. Let's talk about size and timescale, because this is where things get really interesting. There is no reason to assume that intelligence requires a brain the size of ours, operating at the speed ours does, in a body that lives for decades. Consider a creature the size of a continent, a distributed intelligence like a forest, connected through fungal networks, but vastly more complex, that thinks across thousands of kilometers and processes information over centuries rather than seconds. Its thoughts would be incomprehensibly slow to us. A single idea might take 100 years to form, but it might also be incomprehensibly deep. It might hold models of the universe in its mind, if mind is even the right word, of a complexity we cannot approach. Would we recognize it as alive? Probably. Would we recognize it as intelligent? Almost certainly not. We would need to observe it for longer than human civilization has existed to even begin to see the patterns. Now go the other way. A creature the size of a bacterium but colonial, billions of individuals acting as a single intelligence, communicating at the speed of chemistry, thinking thoughts that last microseconds. So fast that our entire conversation right now would appear to it as a geological event, slow beyond comprehension. Intelligence is not a fixed thing, it is a strategy, and evolution finds strategies we don't expect. So what does this mean for the search? It means we might be looking in entirely the wrong places, for entirely the wrong things, in entirely the wrong ways. It means that the absence of radio signals does not mean the absence of intelligence. It means the absence of radio signals from civilizations that use radio. It means that life could be far more common than the silence suggests, and far stranger than we are equipped to recognize. And it means that if we ever do make contact, genuinely, verifiably, unambiguously make contact, the most important question won't be where they're from, or how they got here. It will be whether we have enough in common to even begin to understand each other, because we might meet something that is by any reasonable definition intelligent and have no more ability to communicate with it than a tree has to communicate with us. That is not a reason for despair. It is a reason for humility and for genuine, serious, open-minded curiosity. The universe is not going to give us what we expected. It is going to give us something stranger, something we have to stretch to understand. And if we're willing to do that stretching, if we're willing to let go of the humanoid assumption and actually think about what life might be, then the search becomes something extraordinary. Not a search for ourselves, reflected in the stars. A search for something genuinely other. Something that will change us simply by existing. In my next video, I want to tackle the question of whether we could actually communicate with an alien civilization, even if we found one. Because as we've just seen, the communication problem might be far harder than the discovery problem. SETI, the wow signal, the mathematics of making contact, and the deeper question, if they sent us a message, would we even know? That's next time. See you then.